Okay, good afternoon everyone. Thank you for coming back. Are you guys tired of me? Seeing me all the time? Maybe I promise to leave you in 20 minutes, 25 minutes and not come back until tomorrow morning, okay? Okay, so I'm going to talk to you about ultra high performance concrete. It's also called reactive powder concrete, which is a very high strength concrete that we have developed for connections for bridge decks. So what happens is you have bridge decks, and bridge decks are connected using conventional concrete. So even when you have precast bridge decks, you bring those precast bridge decks in and then you connect them with concrete poured in situ to get those connections, or you connect them with steel. Problem with steel is that in a bridge deck typically, and especially if you have in the US when it snows, you put in salt in the bridge deck so the steel connections corrode. If it's concrete connections, the connections are not very strong, and therefore under repeated fatigue, especially those connections, they start to fail quickly. So the Department of Transportation in Arizona wanted us to develop cheaper ultra high performance concrete formulations. Lafarge sells a UHPC called ductile. You must have heard that in India. And ductile costs around $3,000 a cubic yard. Okay, when a conventional cubic yard is a little lower than a cubic meter, a little smaller than a cubic meter, about 0.9492 cubic meters, $3,000 a cubic yard, whereas a conventional concrete you can get for $100 a cubic yard. So ductile charges 30 times more for this ultra high performance concrete proprietary mixture. So we developed something for a fraction. We developed our own ultra high performance concrete for about $500 a cubic yard. So 1/6 of the cost of ductile, without using any of that fancy materials like quartz powder and this and that. We used only locally available materials and the whole idea based on what I talked in the morning on particle packing. Okay, so UHPC about 120 to 150 MPa strength. When you reinforce it with steel fibers, 1.5 to 3.2345%, they exhibit very high tensile strengths and very high flexural rigidities. They become strain hardening so that you can use it for high-end structural applications. Downside is the cost, as I said. So critical to developing cost-effective UHPC is really rational methods where you create a very dense microstructure. So basically what we have done is microstructural engineering to develop UHPC. So here is a picture of a bridge connection being poured. So you have two precast panels, and then in between you see that a lot of connections have already been poured. Two precast panels, very heavily reinforced, and then you need a very workable mix. A self-consolidating UHPC is what you want, so that you can just pour it because you can't really vibrate it in any other fashion. So you need a self-consolidating mix. So you need very good quality control, extremely good quality control in selection of materials, in mixing. It requires really long mixing time, very high dosage of superplasticizers, very low water cement materials ratio. So whatever I'm going to talk about is about 0.18. Water cement ratio of 0.18. Tends to be proprietary mixes tends to be very expensive, so we need an alternate solution. So here are the materials that we have used. We haven't used all of them in all the mixes. OPC 11.2 microns as median size, slag 8.9, so fine slag, fly ash 17.9 microns, metakaolin 5.3, limestone of 3 microns and 1.5 microns, and we use silica fume also. So all of these different materials, again the idea is use all these different particle size distributions to come up with an ideal particle size distribution to cover a wide range of sizes, so that you get really compact dense mixes. So we initially started with cement, fly ash, silica fume, slag, metakaolin and limestone, created a large matrix of mix, about 33 mixes, cement replacement level up to 30% by mass. We've even gone up to 50% effectively. We started with a water binder ratio of 0.24 and then went down to 0.18, and high range water reducer of 1.25% solids by mass. That translates to about 5% of superplasticizer by weight of cement. Very high amounts of admixtures.
This limestone was used in what form?
Powder. Limestone powder. I've shown you in the previous one here. 3 micron powders or 1.5 micron. So this is 3 micron powder, this is 1.5 micron powder, really small powder. Okay, so you have all these mixes. The idea that we used was you combine them, you create the particle packing, the packing idea that we talked about. So we created a computer model where we can throw in all those particles and find out where each of those particles are and how they will all pack nicely. So the blue is, I don't know what the blue are, but generally you have the white being cement, blue probably is fly ash, the red ones are metakaolin, the green ones are limestone. So you have all those different combinations of materials. And then we want to, because this mixture wanted to be really, really fluid, flowable, we wanted to check for rheology also along with that, because your water cement ratio is 0.18 and you really needed very good workability. So all mixes, particle sizes ranging from 0.1 microns to 50 microns. So we created a representative volume, three-dimensional volume, by filling particles so that we can try out a large number of combinations based on the PSEs. So this was a computer program that one of my students wrote. It's called a recursive packing model. People have done it before, but we did it slightly differently, because basically what you do is you throw in particles into, so you tell what particles have to be filled, how much of each of those particles have to be filled. The program automatically picks a particle, puts in a certain location in the cube, then picks the next particle, and then it keeps on picking particles until the cube is full. And then if the cube is full, then it will pick the next particle, and whatever is the next particle, according to the proportions that you've given, if it doesn't fit, it will try to rearrange the other particles and fit it. So it will go through a recursive algorithm, and it will go through probably 1 or 2 million steps like that to come up with a complete packing, and tells you what is the packing fraction. So we consider all particles as spheres for sake of ease. Angular particles will take a lot of time to do these models.
So, these particles that computer takes, they are unreacted, right?
These are all, yeah, this is fresh state. This is fresh state. Yeah. Packing always happens in fresh state.
That volume might change.
So what? If I get the maximum packing to start with, I'll get the maximum packing to end with. So I don't, because what you need is the densest possible microstructures. But again, remember, there is space between these particles based on the water cement ratio that you've chosen. So the amount, there's place to react also, because your water cement ratio, you have a certain amount, right? Okay, so you have 3D volumes that we have generated, digitized microstructure, and then we come up with 3 different parameters of the microstructure. So first one is called the mean centroidal distance. If I have 2 particles, what is the distance between the centroids of both the particles? So you measure the distance between centroids of all the adjacent particles in the microstructure and come up with one representative mean centroidal distance, which means if I have really, really small particles, they will be close to each other, right? Then mean centroidal distance will be lower. If I have large particles, mean centroidal distance will be larger. So this distance will give you an idea of what is the size, the distance between particles. Now, why is the distance between particles important? Because reactivity is governed by distance. The fly ash has to react with calcium hydroxide. It has to have a certain proximity to react. So that's one thing. The second one is coordination number. How many particles are touching any given particle at any given time? Again, a measure of reactivity. And the number density is the number of particles in a unit volume that tells you how much of filling you have. Okay, and then we came up with different models that relate centroidal distance, number density, and coordination number. We also came up with the packing coefficient, which is the product of coordination number and number density divided by centroidal distance, so that you can make this maximum to get really good packing. And then we did plastic viscosity and yield stress using rheometers for rheology, and then mini slump values. So these are just the compressive strength of the 0.24 water cement ratio paste. You got to only 120 megapascal, and these are for the paste. So only up to 120 megapascal, but we are okay because this was the paste with the 0.24 water cement ratio. Then we started to mix the aggregates. Now, normally in UHPC people don't use coarse aggregates; they use only sand. But the problem with using sand is that shrinkage is going to be a problem. When you have a higher cement plant, shrinkage is going to be a problem. And then if you use coarse aggregate, the structure is going to be more stable. The aggregates are more stable. So I wanted to use coarse aggregates. I said I have to use coarse aggregates and we'll design it that way. So this is among, I haven't seen many UHPC publications or any applied UHPC projects where people have used coarse aggregates, but we have indeed used aggregates that are passing 4.75 millimeter retained on 9.5, passing 2.36 retained on 4.75, and passing 2.36 retained on 1.2. So we have used those, and then we used a coarse sand and a fine sand. Coarse sand is 600 microns, fine sand is 300 microns, or 800 and 400, one of those. And then we use steel fibers. We use what's called a compressible packing model for proportioning aggregates, and I'll talk to you about what that is. And then we created a space in which we can start to select the optimum proportions of these aggregates based on maximum packing density. So compressible packing model. So you have, again, I showed this in the morning. So if you pack particles one by one and change the sizes, again I have shown only one size, but you can have multiple sizes. Even then, you get your maximum packing fraction is 91%. Randomly, if you start putting in a microstructure, what you can get is 70%, but that's not enough for us, right? 70% is not. So you have to go to a higher value. So if you use multiple sizes, then you can go all the way up to 0.84, which is actually good. So basically, what we have is mono-sized particles versus multiple particle sizes. But these are carefully selected particle sizes. Particles have been sieved for all the sizes so that you know exactly how much of what particles are there. And that's where the cost increases, because you have to employ somebody to sieve this and separate the aggregates and store them and all that. And a normal ready-mix operation cannot do this unless they are given more resources. So in a concrete mixture, aggregates cannot be placed one by one, so you have to get virtual maximum packing density. So you have to do it through compaction and vibration. That's why you compact, right? You compact and vibrate, because just by placing, you will not get maximum density. So we use 5 different classes of aggregates, and we use steel fibers 0.6 mm diameter and 13 mm long. And these are the aggregates, and we had to wash and clean so that the aggregates are really clean. Remember, every little impurity, every little defective spot is going to cost you when you're looking at very high strength concrete. When you look at 150 megapascal, it becomes tougher and tougher. You can get to 80, 90 without too much of a problem. Once you get beyond that, every single MPa is painful. You start to, every little increment, you have to be very, very, very careful. Okay, mechanical splitter was used, so we got all these aggregates. And then we did a compressible packing model. We used dry rotted unit weight, got the combined size distribution of the aggregates, put it in the model, got different packing densities for different combinations. I'll show you in the next slide. A lot of different combinations. I think we did 885 combinations. And again, like I said, I cannot afford to do 885 combinations in the lab. I don't have the time, I don't have the money, I don't have the energy. So this was all computer generated. So we all did computer simulations to do that. And the best density was a 0.696 packing density. It's only aggregates, okay, no cement paste here. 40% of number 4, 10% of number 8, 10% of number 10, 20% and 20% of fine and coarse sand. 0.696, that was the aggregate combination we used. And then so you can see with all these combinations where the maximum packing densities are, so we can pick it up from there and use the packing densities. So these are the common aggregates that you can get in the US. So they call by, I don't know how it is in India now, but they typically do by these numbers. Number 57, number 68, 78, 89. These are the typical seed numbers of the aggregate sizes. 57 is very common, but you get a packing density. Typically, look at typical packing densities of those aggregates, right? If you do that, if I choose a standard 57 number stone that they use for regular concretes, my packing density is only 0.55 to 60. 89, I get up to 66. But here I get up to 0.696, which is the higher packed density. And then you put in fibers, and when you put in fibers in an already packed mix, the packed density goes down because these long fibers try to push the aggregates away, right? So they create more space. So you have to account for that also. So here are some of the pictures of concrete. Look at how flowable the concrete is. This is even with fibers, and you get a 355 millimeter slump flow, which is effectively a self-consolidating concrete. So this is self-consolidating concrete with very high strength. Okay, so now if you look at it, you can get 28 day strengths of up to 160 megapascal for a mix with fly ash, microsilica and limestone. That's it. 17.5% fly ash, 7.5% silica fume, 5% limestone and OPC. That's it. So 30% replacement of cement, you get about 160 megapascal. Here is a mix with 50% replacement of cement, 30% limestone and 20% microsilica, 20% silica fume, you get about 140 megapascal strength in 28 days. Again, because you have fly ash in these mixes, you will know that at 90 days this will be even higher, right? So I'll show you, I think I have that data. And this is the failed cylinder, and you see real nice shear failure. Okay, now